Complete and net ionic equations show us more closely what is going on in a double replacement reaction. You, of course, always have to start with a balanced chemical reaction. The chemical reaction that's given is balanced. And then the complete ionic equation is going to list all the ions present as either reactants or products. The ions are in the substances that are aqueous, because aqueous means that it's dissolved in water, and when ionic compounds are dissolved in water, they break into individual ions. So anything that's aqueous, we are going to split apart, and we are going to write as ions. Anything that is not aqueous, we are going to leave together. It's really important that you have the correct coefficient and charge on every one of your ions. So this is lead 2. Lead can be a 2 or a 4, but we know it's lead 2 because it's bonded to 2 nitrates, and nitrate is -1. Plus, there are 2 nitrates in this formula, so that's how I write my ion, 2 nitrate ions. Plus, coefficients, of course, distribute, so 2 potassium ions and 2 chloride ions. The lead 2 chloride, that's a solid, so we do not split it into ions, only split aqueous things into ions. And then again, the 2 will distribute, so I have 2 potassium ions and 2 nitrate ions. Notice that on both sides of the reaction, potassium and nitrate are written as ions. So from the reactant side to the product side, they don't change at all. Nothing's really happening with them. There's a special name for those. Those are called spectator ions. So spectator ions are ions that are unchanged on both sides of the equation. The net ionic equation only shows the species that actually change, so it gets rid of those spectator ions. So if I, again, really quickly write my complete ionic equation, I know that my spectator ions are potassium and nitrate, so I can get rid of them and rewrite what's left over. So lead 2 plus 2 chlorides yielding lead 2 chloride. That's what's called my net ionic equation. It is really just showing the formation of the precipitate or the formation of water if it's a different kind of reaction. So we're going to write a complete and net ionic equation for this reaction here. Again, coefficients are going to distribute. So I have 3 strontium ions, and I have 6 chloride ions because of the coefficient of 3 times the subscript of 2. I have 6 lithium ions, and I have 2 phosphate ions. I do not write the strontium phosphate as ions because that's solid, so you only again split up aqueous things, plus 6 lithium ions plus 6 chloride ions. When I look at this complete ionic equation, I can see that the chlorides are spectator ions and the lithiums are spectator ions. So I'll cross them off, and then I will rewrite what is left over. And that is my net ionic equation. And your spectator ions should always cancel out. There should always be 2 of them, and they should always cancel out. If they don't, something went wrong. So again, I'm going to write a complete and net ionic equation. I have 2 hydrogen ions plus 2 iodide ions plus a barium ion plus 2 hydroxide ions. I'm not going to split up the water. The water is liquid. Liquid is different from aqueous. So those H2Os are together as H2O. They are not separated into ions. Looking at this, my spectators are going to be the iodide and the barium. And I'd be left with 2 hydrogen plus 2 hydroxide, yielding 2 water. Now, notice we got coefficients of 2 in front of everything, and we know that in a balanced reaction, it always has to be in the lowest ratio. So my actual net ionic equation is just hydrogen plus hydroxide yielding water. This reaction that we just did is called an acid-base reaction. An acid-base reaction is when we have an acid, which is some compound that starts with hydrogen, and a base, which always, for now, will end with hydroxide. So we have something that starts with hydrogen reacting with something that ends with hydroxide, and you will always form the same products in an acid-base reaction. You will always produce water, and you will produce salt. Salt is any ionic compound. So this one happens to be sodium chloride, but it could be magnesium bromide. It could be lithium phosphate. It could be iron 2 carbonate. It's any ionic compound is a salt, and that will always be one of the products of an acid-base reaction. When we are doing complete and net ionic equations for acid-base reactions, it's really the same as doing them for precipitation reactions. It's just that you have water that you don't split up as opposed to a precipitate that you don't split up. So we have sulfuric acid, which is H2SO4, and sodium hydroxide, and those are both aqueous based on solubility rules. That's going to form water, and which is liquid. Water is always liquid in this reaction, and sodium sulfate, which is my salt, and based on solubility rules is aqueous. Balancing this reaction, I need a 2 in front of the sodium hydroxide and a 2 in front of water. Yep, that balances. And then writing my complete ionic equation, split everything up into ions. H2O plus 2. My spectator ions here are sodium and sulfate. And so my net ionic equation, 2 hydrogen plus 2 hydroxide yields 2 waters, which again can reduce to hydrogen plus hydroxide yielding water. It's not a coincidence that both acid-base reactions had hydrogen plus hydroxide yielding water as the net ionic equation. In fact, this is always the net ionic equation for acid-base reactions because they always make water and salt, and the salt will always be aqueous. So it's a net ionic equation for an acid-base reaction is always going to just be forming or showing the formation of water.